Alright class, so let's start with the topic. Between Dtft and DFT, right? So let us do one thing. Let us divide this page into two part. One thing, you studied your DTFT. Okay, so we are not going to get into the details, but how we got DFT, right? So for DTFT, we have x of omega minus infinity to plus infinity, x of n e raised to the power minus j omega n, right? So my omega, which is my angular, my omega varies from 0 to 2 pi, right? So let us just see how this omega varies. So this is my omega. Starts from 0 and it takes a complete circle and come back to 2 pi. Okay, so this is my variation of omega, okay, from 0 to 2 pi. Okay, so how do we get there? Now when we are talking about my discrete Fourier transform, what happens is, so this is my omega is equals to 0, omega is equals to pi by 2, omega is equals to pi, and omega is equals to minus pi by 2. Okay, so and this is when omega reaches 2 pi. Okay, so it's from 0 to 2 pi. Okay, now where we can say x of n is in my time domain, and when I've done DTFT, I get x of omega in frequency domain. Okay, but the point is the value of omega is still continuous around this circle. Now when we go for DFT, here what I do is I play with this omega, where this omega is being replaced by k by n, where n is number of samples in which we are going to divide or calculate the transform DFT. Okay, so let us take an example. Let us take n is equals to 8. Okay, so what I'll do at first instance, for k is equals to 0, okay, we'll just make a table out of it before moving. Let's try and form a table. Right, so k is equals to 0, 1, 2, 3, 6, 7. So total 8 values. So what will be the value of my omega? For k is equals to 0, my omega will be 0. For k is equals to 1, my omega will be pi by 4, that is 2 pi by 8, 4 pi by 4. For k is equals to 2, my omega will be pi by 2. For k is equals to 3, it will be 3 pi by 4. For k is equals to 4, it's going to be pi, and so on. Okay, so what I have done basically, so if I'll just, what I'll do is, just give me a sec. Okay, so basically what I've done, I've taken the samples. So my first sample, I'll mark it with red color. Okay, just wait. So my first sample will be at omega is equals to 0. My second sample will be at omega is equal to pi by 2. Third sample at omega is equals to pi by 4, pi by 2. So basically what I've done, I've taken the samples of omega and I've recovered back my DFT, that is x of k 0 to n minus 1 x of n e raised to the power, in DFT, from DFT where I had e raised to the power j omega n, I'm going to replace this omega by 2 pi kn. So it's 2 pi kn. Just write it again for you. X of k one x of n e raised to the power minus j 2 pi kn. Okay, now this is my ID DFT, so you need to remember this. So the relation between DTFT and DFT is, in DTFT, if I replace omega by 2 pi k capital N, then it forms my discrete Fourier transform. Similarly, for recovering back from discrete Fourier transform, so what all pairs I have? Okay, I forgot to mention the limit of k 0 to n minus 1. Always remember class, you cannot forget to mention this limit where k is. Okay, so you need to remember the two formula in its very true form. So the most important formula, as discussed earlier also, my DFT, that is x of k n is equals to 0 to n minus 1 x of n e raised to the power minus j 2 pi k n by n, where k is equals to 0, 1 to n minus 1, and IDFT x of n is equal to 0, it's this time it's k is equals to 0 to n minus 1, 0 to n minus 1 x of k e raised to the power j 2 pi k n by n, where n varies from 0 to n minus 1. Alright class, so you need to remember these two formula. Now on the basis of these two formula, we are going to evaluate all the values. Okay, so let us start with the first. Okay, we'll do the numerical in the next video. Thank you.